Hi, my name is Jacqueline, and I'm going to be presenting on the synthesis of bifidenone. So first, I'm just going to talk a little bit about what bifidenone is and what it can be used for. Then I'm going to go over some of the special features of this molecule before taking you through the retrosynthesis. It's going to be 12 steps, and I will go through 6 of the steps a little bit more in detail. So what is bifidenone? Bifidenone is a natural chemical that is found in plants of the genus Bioschmiedea. Before the total synthesis of bifidenone was developed by Zhongping Huang and his team, that's the paper that I'm presenting on, by the way. Before they came up with the synthesis, only 79 micrograms of the natural compound has ever been isolated. So it's a very small amount and is not enough to move forward with studies and studies pertaining to the compound and its potential as a cancer drug. So bifidenone is known to have anti-proliferative properties, meaning it can inhibit cell growth. It acts as a tubulin polymerization inhibitor, which basically stops the process of forming microtubules from tubulin, which is necessary for cell structure and growth. Microtubules basically make up the cytoskeleton. So what it does is it disrupts the G2 and the M phase of the cell cycle by stopping the production of microtubules, and this in turn stops the division and multiplication of cells, which can be really helpful against cancerous cells. So now that we know the potential of bifidenone as a cancer drug, now we can understand how important the development of the synthesis is. The synthesis of bifidenone is a 12-step synthesis starting with commercially available 1,4-dioxyspiral 4.5-decanadone. Some of its unique features include the dihydrobenzodioxylone ring system, which is this picture that I included here, or this compound, and the sterically crowded cis-configured allo and aeropropyl substituents. There are also 3 stereocenters that require the use of admixed beta dihydroxylation, followed by a palladium catalyzed decarboxylation allylation. So I will talk more about the admixed beta dihydroxylation later on. There's also been previous attempts at the synthesis of bifidenone, but they were always halted at the preparation of the dihydrobenzodioxylone ring system. Terashima and his team used paraformaldehyde and catalytic D-alkaphosulfonic acid in cyclohexane to generate the ring system, or to try to generate the ring system, while Danishevsky and his team tried a photo-induced rearrangement using UV irradiation, but both of these methods fell short of producing this dihydrobenzodioxylone ring system. Now let's look at the retrosynthesis of bifidenone. So we're going to start from the commercially available chemical, and we're going to work our way all the way to bifidenone. So it's going to be 12 steps. Just really quickly, going to run through each step before we look at a few of the mechanisms later on. So first, we start with a Gringer's reaction, and we're going to add this group onto this carbon. So from there, we have a hex reaction to add this group onto the alkene. Next, we want to do a catalytic hydrogenation, and this is going to get rid of the double bond by adding hydrogens across the alkene. And from there, the alcohol is going to be protected, and we're going to change it to benzyl ether. Once that one is protected, the other alcohol is going to be eliminated, and we're going to form a double bond where dihydroxylation is going to occur. So it's going to be syn dihydroxylation. The OH are going to be on the same side. From there, we protect it by adding in an aldehyde and cap off the diols. And then we want to separate the enantiomers. So we separate one of the enantiomers out, and we get this one with that enantiomer. And then from there, we want to change the benzyl ether back into the alcohol, and then we change that into a methoxide group. So it could be some sort of esterification. From there, we add this group here through an enolate reaction. So we're going to have an alpha hydrogen, and we're going to add this group. And the last step is going to be a decarboxylation allylation. So the first mechanism that I'm going to go over, or the first reaction that I'm going to go over, is going to be a simple Grignard's reaction. So we're going to start with the bond between the carbon and the magnesium bromide, and it's going to attack the electrophilic carbonyl carbon and push the electrons from this double bond here onto the oxygen. We're going to end up with a negatively charged oxygen here. And this group here is from the Grignards. And then we just want to protonate the oxygen with water, and we end up with this intermediate. For the Heck reaction, we start with the active catalyst, and then we add this Rx group. So this is the X, and then this whole section here is the R, onto the palladium. Next, syn addition occurs, with the R group adding to the side with the least substituents. So we have the R group here, and is on the side with the least substituents. And we're adding across this alkene right there, by the way. After the syn addition, we want to make sure that the palladium and one of the hydrogens are on the same side before syn elimination occurs. So in this case, we would rotate this bond right here so that the palladium and the hydrogen are on the same side. And then once we eliminate, we'll end up with our product right here. And that's one of the intermediates for the reaction, or for the formation of bifidenone. Next, we have catalytic hydrogenation, which is when hydrogens are adding across the alkene to get rid of the double bond. So if you remember, the metal catalyst is actually going to be in a solid phase, and the catalysis happens on the surface of the metal. So the hydrogen, the H2, is going to absorb onto the surface of the metal, and the HH bond will break. Then the alkene comes in, attaches to the metal surface, and then the two hydrogen atoms will be transferred one by one to the pi bond of the alkenes before it is released from the surface of the metal. So when it's released, it's going to be hydrogenated. So it's going to be an alkane. It's no longer a double bond. Next, we have two reactions here. The first is going to be a conversion of alcohol to alkyl halide using SOCl2, and we're going to follow that with an E2 reaction. So first, the electrons on the alcohol are going to attack the sulfur and kick up the electrons from the double bond to the oxygen. And this forms a new sulfur-oxygen bond. And then next, we have the electrons from the negatively charged oxygen come back down to reform that double bond. And chlorine is a good leaving group. So one of those chlorines are going to get kicked off. And that's going to form our chlorine ion that's going to come back in later. Next, pyridine comes in to deprotonate that positively charged hydrogen, and then we're left with SO2Cl, which is a good leaving group, and chlorine is going to come in and kick off that SO2Cl. So that's how we get our alkyl halide, and that's the first reaction. Next, pyridine is going to come in and perform an E2 reaction this time, and because pyridine is hindered, we're going to form the less substituted alkene. So it's going to grab that hydrogen from the less substituted side, and then that hydrogen or those electrons are going to form a double bond, the alkene, and kick off the good leaving group, which is the chlorine. So before I get into the mechanism for admix beta, I'm going to just talk about it a little bit. So admix beta dihydroxylation, AD just stands for asymmetric dihydroxylation, and it's also called sharpless asymmetric dihydroxylation. In this reaction, hydroquinidine 1,4-thiazine-diol diether is going to be the ligand that comes in. The reason why we use this admix beta instead of osmium tetroxide or KMNO4 for syn dihydroxylation is because this one is enantioselective and is going to give us a certain enantiomer. I will show you in a moment. This particular synthesis, they use methane sulfonamide, and this is to improve enantioselectivity, and it also speeds up hydrolysis. So this reaction actually produces 2 enantiomers, but it's going to favor one more than the other. For the mechanism of admix beta dihydroxylation, we're going to start with osmium tetroxide. And then we have this intermediate here from the synthesis, and then the ligand comes in. So remember earlier I said the ligand was dihydroquinidine 1,4-thiazine-diol diether. So that's going to attach to the osmium tetroxide, and all of that is going to add to this alkene right there. Throughout the mechanism, these two R groups are going to stay trans to each other. So it's also trans right here, and right here it's trans as well. One's coming forward and the other one's going back. It's a little bit hard to see. And then this one is also going to end up trans to each other. For this step in the middle right here, we just have an oxygen coming in and the ligand is going to get kicked off. And for the last step, we have water coming in to kick off the osmium tetroxide, and that's going to form our syn dihydroxylation. So this step is going to set up this this stereocenter right there and this stereocenter as well for the synthesis of this molecule. The enantiomeric purity of this molecule, the product right here, is going to be 76%, so that's pretty high. So for the last reaction, we have the reaction of an allyl halides with enolates. So LEA is going to come in and attack the alpha hydrogen, and then we have the electrons kick back down to reform the double bond, and then the electrons from the double bond is going to do an SN2 reaction, kick off the bromide, and the allyl group will attach to the compound. So this gives us the trans isomer. If we want the cis isomer, we have to attach an ester group to the compound, and then we would do a palladium catalyzed decarboxylation allylation to get the cis isomer.